In this video, we're going to do a walkthrough of the CHEM 1411 experiment called Molecular Modeling in the VSEPR Theory. So what you want to do before we actually walk through this is go back and watch the lecture videos from Chapter 7 and Chapter 8 to review the concepts that are going to be covered in this lab. The things that you need to turn in are all of the problems in the report form and the post-lab questions that are in your lab manual, and then submit those via Blackboard. So let's go through how we do one of these problems. So there is an example problem already completed for you, and that's the carbon dioxide problem. And essentially there are multiple components that I'm wanting you to practice and do. We're going to give you the molecule, and then I want you to go through the NASA table and determine the number of bonding pairs and lone pairs that are going to be in that molecule. Then here you're going to draw the Lewis dot structure itself. I want you to determine the electronic geometry or electron pair geometry of that Lewis dot structure by telling me how many numbers of areas of high electron density there are, and then just giving me the name of the respective electron pair geometry shape that is associated with that. Then through the number of lone pairs, you're going to tell me what the molecular structure or geometry happens to be for that molecule, and you can just again give me the name of that shape. Then tell me what is the hybridization of the atomic orbitals for the center atom. And that again, you'll use the areas of high electron density to determine. And the last thing that I want us to do is determine whether or not this molecule is polar or not. And I've given you a series of questions in order to help you determine this polarity. One of the questions is whether or not the molecule is symmetric. And what we mean by symmetric is it symmetric in the molecular geometry, not the Lewis dot structure. So make sure that you're looking at the molecular geometry while you're assessing that. And symmetric, what I mean is, can you turn the molecule in multiple angles and it look like a mirror image of itself? The other question that I have here is, are the same end groups present? End groups meaning the same atoms at the ends of bonds. If you have different atoms within a center atom bonded, even though they're single bonds, those atoms are most likely going to have different electronegativities. Therefore, the molecule would be polar. So one thing that you can say is that if you answer yes to both of these questions, then the molecule will be nonpolar. However, if you answer no to any one of them, that molecule is polar. So this is one easy way to look at the structure itself and determine whether or not it's polar or not. So let's go through this practice for carbon tetrachloride, and we'll show you how this works out. So we're going to start with the NASA table. You have carbon and chlorine, and for every one carbon it wants 8 electrons, and all 4 chlorines want 8 electrons, and that's a total of 5 times 8, which is 40 electrons. Then you have your one carbon has a total of 4 valence electrons from group 4, and your 4 chlorines have 7 valence electrons, and so that's a total of 32. Then you're going to take 40 and subtract 32, and that'll give you 8. And then you'll take 32 and subtract 8, and that gives you 24. And we'll divide both of those by 2, and that will tell you that you have 4 bonding pairs and 12 lone pairs that are in that structure. So let's start with the skeletal structure of carbon tetrachloride. So you'll have carbon as your center atom, and I'm going to put all 4 of my chlorines in one of my north, south, east, west quadrants. And then what I'm going to do is I'm going to check and make sure that the number of bonding pairs I've put in my skeletal structure match, and it turns out it does. So we've checked off the bonding pairs and we don't have to worry about that anymore. What about the lone pairs? When we have 12 lone pairs, we check with the center atom first. It already has an octet, so we move on to the end groups or the atoms that are attached to those bonds. And it turns out that each one of these chlorines requires 3 more lone pairs, which totals up to 12. And so that would give us the completed Lewis dot structure. So we are done with that. So now what we want to do is look at the molecule itself and determine what its electronic geometry and molecular geometries happen to be. So if we look, it turns out that there's 1, 2, 3, 4 areas of high electron density attached to carbon. And 4 areas of high electron density in electronic geometry world is a tetrahedral shape. None of those areas of high electron density are lone pairs, so we'll say that's 0. And anytime this number is 0, the molecular geometry is the exact same as the electronic geometry. So that is a tetrahedral. I'm going to go ahead and look at the hybridization, and I'm going to look at the SP, or the hybridization of the center atom. And since it's 4 areas of high electron density, I know that this is a hybridization of the center atom of sp3. And then I'm going to look at the symmetry. Now, this again, you need the 3D structure to be able to ascertain these things. So it might be easy for you guys at home to use the PhET simulator. And so I'm going to build the compound carbon tetrachloride. So I have 4 of the same atoms on the ends of single covalent bonds in a center atom. And so I know that my electronic and molecular geometries are again tetrahedral. And what I'm going to do is I'm going to look and I'm going to turn this around in various angles that you can see here. And every time I turn it where, say, an atom is in the north position, I can look at that and I can go, hey, I can cut that in half and it looks like a mirror image. So in this particular case, I would say that yes, that is symmetric. And the same in groups, all of the atoms at the ends of these covalent bonds are all chlorine atoms, so they're all the same. So I would say yes. And since I said yes to both of those answers, my molecule is a non-polar molecule. Okay, so this is what you would do. Go through all of the rest of the problems within your report form and answer the few post-lab questions that are after that. There's some additional pieces of information that I do want you to know to remind you about. Don't forget that your ions, there's several ions in this packet that need brackets, and the charge that's associated with that ion also within the Lewis dot structure. So don't forget those. That's a part of the structure itself. The second thing is that if you happen to have something that has resonance structures, so you could draw multiple versions of that molecule, just choose one and draw that. You don't have to draw all of them. One Lewis structure would be perfectly fine. And then there are 3 molecules that I wanted to just point out some things about them that are unusual that just with an experience you would become familiar with, but I just wanted to point them out to you right now. And that's that there's one molecule called S2O3 with a 2- charge. And the statement underneath this molecule says that choose one sulfur to be the center atom. Well, I'm going to go ahead and draw the skeletal structure for you. So you have a sulfur in the center atom, and then you have your second sulfur attached to that, and all the rest of the oxygens are all also attached to the sulfur as well. So this is your beginning of your Lewis dot structure. You would have to add any additional bonding pairs or lone pairs that you might calculate from your NASA table. The second molecule I want you to look at is this one called Mercury One Bromide, and so, or Mercury 2 Bromide, sorry. And this particular molecule has a transition metal, and that's okay. There are some molecules that have transition metals that have covalent-like properties and will form covalent bonds, and this one is one of those. So I need to kind of tell you what the rules are for this particular element with regards to how many electrons it wants in its outer shell to be happy and how many valence electrons it has. So this guy does not follow the octet rule. Instead, it wants a total of 4 electrons. So on the N category for the NASA table, you would use the number 4 instead of 8. And the number of valence electrons it has is 2. So it has 2. This compound down here with xenon, so it's XeF4, is a noble gas. And so this is a little weird to have a noble gas bonded to some things and other elements, and that can happen under certain conditions, and this is one of those molecules. But I just wanted to reiterate to you some things about the NASA table calculations that you'll need to be able to do. One is that its octet, it does actually follow the octet, and so its N value is going to be 8. But see, it's already a noble gas, and so since it's a noble gas, it already has 8 valence electrons. So the first A number in your NASA table is also going to be 8. So make sure that you pay attention to these numbers here when you're doing these structures, because that will affect your NASA table and your overall structure in the end if you're not paying attention to that. So this is the end of this video for your molecular modeling and VSEPR theory lab. Please go in and complete all of the rest of the Lewis dot structures and the information that goes along with it in the post-lab questions and submit those via Blackboard.